Before moving into putting everything together and building a whole system, including the MMIO and the video subsystems, I want to talk a little bit about clock management. So in the enhanced synchronization circuit and the core itself, the synchronization core we placed into the video subsystem, we utilize two clocks here. One is 100 megahertz and one is 25 megahertz. I've showed you in a previous code that it's very easy to generate 25 megahertz out of 100 megahertz because it's just 1/4 of it. However, the synchronization core we placed into our system is so robust and it should be able to actually accommodate different resolutions. And if we're accommodating different resolutions, we're going to change these two numbers and that will not be 25 megahertz anymore. It'll be something different and it will be a little bit more difficult to generate it out of the 100 megahertz. So we need something a little bit more robust to follow our design, our robust design. So when I've showed you the whole system before, I've actually always included this particular block here, which is the clock management circuit. And if you probably remember, anything that is in gray, it's actually already built. We're not going to build it from scratch. We're not going to write Verilog code for it. As it turns out, the Xilinx has proprietary macro cells, like the BRAM we've seen and like the XADC we've also seen. It also comes with a clock management circuit. And the clock management circuit basically generate different clock frequencies, and it's a lot more robust than the onboard clock. You will still need an onboard clock to drive everything, and you will see shortly that we're actually going to provide that clock management circuits with a 100 megahertz as an input in here. So we're going to put the 100 megahertz from the board, but we'll generate several other clocks in here, and you can generate many of them. And it's a lot more robust. The outputs of these of this clock management circuit is a lot more robust because it has a closed feedback loop, and it will also, you can actually generate 100 megahertz, and that 100 megahertz for some reason happened to be a little bit more robust and more stable than this 100 megahertz. But because of this feedback loop, because of control theory, you're gonna have to wait a little bit for it to stabilize. So there's a short period of time at the very beginning when you initialize the system when these clocks are not ready yet. And generally speaking, what we do is we connect that the output, like it tells you, that circuit tells you there's actually a locked state, and we usually connect it to the reset or the inverse of it to a reset. So let's see how we can actually utilize this clock management circuits in code. So we're going to go to Vivado in here, and I will go to the IP catalog. And as usual, I'm just going to actually look for clock. And as it turns out, we have something we call a clocking wizard. So the clocking wizard actually, once it starts, it'll basically give me a wizard that I can actually go through to see what we can do. So in the clocking wizard, I can just basically go in here and just give it some sort of a name because it expects a certain name so that it actually fits within the code I'm actually giving you. So I'm gonna use MMCM Pro. That's the name that we're gonna give it. And we're going to go to the clocking options. So in the clocking options, I will tell it basically that your input is actually the clock in. I'll just basically call it 100 megahertz. That's basically what I'm going to call it. It's basically the clock that comes from the board. Okay. And we're going to be using the MMC. There's a couple of technologies that generate different clocks. We're just going to be using the MMCs. The phase lock loop is another example. You can actually check that. Or basically read the documentation to see the differences. It's really interesting. For the output clocks, this is actually what's useful about it in here. So the output clocks, you can actually generate a bunch of them, actually up to 7. So we're going to actually generate 4 of them here. So to follow our diagram. So for example, the first one is going to be clock, and I'm just going to call it 100M. Okay, and you can actually tell it, well, I'm going to request 100 megahertz as the output. So the input is 100 megahertz, and the output here, the first output I'm going to decide is actually 100 megahertz. And the reason why we're doing that, it's a little bit more stable. And as it turns out, like when it calculated the way it actually computes it, it tells me that the actual will be 100 megahertz. The second one will be the 25 megahertz that I have been utilizing. So for example, I can go in here and I tell it like I want 25 megahertz. So when I click in here, it actually tells me, okay, I can give you 25 megahertz. I'm gonna generate a couple of others, and these are ready for you in case you need to use other VGA resolution. For example, I think this is for the SVGA. Okay, so which is 40 megahertz because it's a high resolution, so you need a higher clock frequency. So you're going to request 40. It tells you I can give you 40. So the last one in here, I'm going to actually request. It's pretty much 60. Well, let me just write 6 in here and tell you. I need something that is basically 65 megahertz to accommodate something that's called XGA. It's also high resolution. And when you actually request 65, it tells you, well, I can give you 66.6. It's approximately 67, so I'm just going to call it 67 megahertz. It just cannot give me that 65. So this is basically how we generated, and all we have to do is just basically click OK, and it will generate that particular clock management circuit that we've seen here. And now we have all these clocks, all these frequencies, the 100, the 25, the 40, and also the about 67 megahertz ready to your system, and you can actually connect it. And we're going to see these already included in the whole system.